Okay, we're continuing to study Chapter 5, our home planet, planet Earth. It's beautiful, blue dot, 6 interconnected layers. You're learning how they're connected, the essentials, right? What's going on in each layer and how does it affect the other layer. We talked about the 3 interior layers. What's up in each? How do we know? Make sure you can just rattle those off. Details, not too many details, just enough details we went over. And now we're going to talk about the surface and the crust. There are 4 processes that change the surface that we're going to focus on. And as we do that, we're going to look at other worlds too. Once we study this, we'll be able to look at other worlds like Venus, Mars, etc. I might mention a little bit about where water came from, and I might send you out and have you explore that. Then we're going to go to the magnetosphere, and then we'll come back to the atmosphere. Okay, so that's our task right now. Our surface, what 4 ways does it change, or has it changed? And so now I'm going to go over here. Sorry, but I'm going to do this solo. And we're going to take a look at that beautiful blue dot, right? That little speck right there. That's Earth. Looking back on Earth, the Voyager missions. Everything we know happened there. Everyone we've known, everyone that's been that we know of. Looking at Earth a little closer from Moon, we see this. And again, we wonder, what's going on with it? Look at the changes. When you get into chapter 6 and talk about Moon and going to Moon, size makes a huge difference. And as we study different worlds, we'll see that size makes a big difference in how the world is. Think to yourself now, Moon is how big compared to Earth? How many moons can go across the width of Earth each way, right? You know that answer, so I'm going to leave it to you. So taking a look at Earth now, we see Let me bring that in for you? Yeah. And Earth. Think about it. This is a good time to review. Because we're going to talk about that surface, right? We've got the 3 layers inside, hot, solid iron core cannonball inside. Around that, a liquid iron. Remember, Earth is spinning. We'll talk about that again. And around that, metal interior, metal core, mostly iron. You've got rock going out there, hot rock. And we'll talk about that again. And all that inside is what makes things happen on the surface. It also releases the gas for our atmosphere, which is so thin, as you see. Also, on that second layer, the inner core being solid, the outer core being liquid, the spin of that liquid iron creating a magnetic field that goes way out, and we'll talk about that briefly, but of interest. The old space shuttle missions, just to bring the satellites up. You don't have to go very far. Look down at that layer. Earth spinning San Francisco to Washington, D.C. Sunrise across the Terminator. Earth spinning. Sunset across the Terminator. Hubble Space Telescope, like the size of a big semi-truck or so. Solar panels, looking out, way, way out, seeing unbelievably clear images, looking back, seeing things happen, weather happen, lightning happen. We see the cores. We don't have to get that detailed. We can just go into the main layers here, and we'll talk about it. And we know how we know main layers. One of the things is an earthquake. We talked about the S and the P wave. The primary gets there first, the S gets there second. The farther away you are, the longer it takes the S to get there after the P. But S can't go through liquid, so this helps us image that. You can see pictures. You do have to be careful, right, with pictures. Is that real? Did it just go like that? Or is it Photoshop? Huh? You can explore that. And this picture I like quite a lot. And I'll ask you to even pause and think. What are those red dots? Give you a hint, we're talking about the surface of Earth, right? Surface of Earth. So those are something, some changes, something on the surface of Earth. Really guess. If you guess, then when you're surprised, if you're wrong, then you correct that. If you're right, you go, cool. So what are those? What are those? Most people don't guess it. I would guess volcanoes. We'll talk about that. Earthquakes. No. What are those? Let's come back over here. And then let us, let's take a quick tour back in here of what we had done. I missed it. There it is, okay. All right, what have we done? We talked about the three interior layers, heavy metal, hot. Right? We talked about the mantle. What is that? What is it when things, hot stuff, expands, rises, cools, and sinks? What is that? That's with direction, convection, right? So that's convection. Do you think that that would affect the surface? You bet it affects the surface in a big way. So we're going to talk about that. So all this is inside of Earth is affecting what we see on this surface. And we got the atmosphere, and now 4 layers, some water there too, and the magnetosphere that goes way out past that. All right, so let's talk about what affects and changes Earth's surface. What kind of changes did it go through? And so we're going to come back over here and take a look. Those red dots were impact craters. And so the things you need to know about impact, about these processes that change Earth's surface, 4 processes. I like to do this one first because it came first. Not exactly, all this stuff was happening at some time, but as a way of thinking about this, give us some time sequence. Remember in chapter 0, and then we'll see again in chapter 7, our solar system formed way after our galaxy formed. Our galaxy formed after about 1 billion years, half a billion to 1 billion years after the universe came out of nothing. There was nothing, and then there was universe, and there were atoms, and then things clumped up into galaxy kind of clouds, and in our galaxy, lots of stars formed and died, and maybe likely in planets, and who knows, civilizations will. But then eventually ours came to be. Our galaxy formed 13 billion years ago. Our solar system, about halfway out of the center of the galaxy, 4.6 billion years ago. Know that, remember it, do whatever it takes. In the first billion years, we're going to tell this story in chapter 7. You'll see the video. But as the things were forming, a lot of stuff was flying around, smashing into stuff, messy, violent collisions. Most cratering impacts happened during the period of heavy bombardment. But many, many of those we don't see. Why? Why? Think about it. What's the process? Get a simple video in your head, just a sense when you look around, when you see a picture. Have a context. I mean, which got hit more, Earth or Moon? Pause and think about it for a while. See if you can guess. Now, which looks like it got hit more if you look at a picture? Earth doesn't look like it got hit a bunch. Moon does. Here's my moon. But wait a minute. If a whole bunch of stuff is flying around, what's going to get hit more? just randomly flying around. The bigger target. The bigger target. And yet, you see the craters of Moon. You don't see that many craters of Earth. Why? Because the other processes covered up our craters. Why? Because Earth is still warm inside. Why? Because of its size, retaining the heat, and its size, having more radioactive material to keep heating it. Okay? So all this is connected. Those are the connections. That's all. Right? So which looked like it got hit more? Well, you can bet Moon did. All you gotta do is take a look. Binoculars out. Which did? Earth. Why? It's a bigger target. Simple. Stuff flying around. Who's going to get hit more? Okay. If these are the size of Earth and Moon, I'm going to paste it out for you. 1, 2, 3, 4, 5, 6, about 7 long steps. Earth is here. Moon is about 7 long steps. I get 4 across, 4 across, 4 across. I shrink it in all directions, quite a bit smaller, right? Not going to stay warm inside. We'll talk about that. Okay, so craters. Craters happen, but they got covered up by processes. Let's take a look. Let's take a look at those processes here and see what we've got. All right. There's our cratering. But you don't see them on the surface. They've been covered up. But we can do techniques, imaging, to find them. That's a nice crater in Arizona, sometimes called the Barrington Crater or the Meteor Crater. You see there's a building over there. Go to the visitor center, kids will get bored and whatever, because it's hard to imagine this. But then you tell them something from space came in and slammed, creating a hole maybe 10 times wider than the original thing, pulverizing the thing, sending a plume into the air, which travels through the atmosphere, particles. So it's pretty wild. It's a big impact. Now, that wasn't that long ago. I think it was 50 million, something like that. Okay, so there's a crater. There are craters. That one wasn't covered. Now, this is called Crater Lake, and I want to make a point here. This isn't Oregon. It's gorgeous, beautiful, but this is a caved-in volcano. So you get snow, and the snow melts, and you get the lake, but it's called Crater Lake, but it's not an impact crater. I mean, you have rain, and you might have craters forming potholes in the ground from the water, etc. But we're talking about stuff from space coming in and impacting. So not Crater Lake, no. Not the same thing. I mean craters. I mean something from outside of Earth's atmosphere. That's what we mean by space, usually outside of Earth's atmosphere, coming in, right? And slamming Earth and creating a dent. There aren't that many you can cover up. I mean, I just typed this up, looked it up, 3 largest impact craters in the US. How big are they? And where are they? Now you can pause and study this if you like. In the US, the first biggest is the 6th overall on Earth, biggest. Where is it? Virginia. 55 miles across, so think about your region and where that would be. Here would be like here to Sacramento, the San Francisco Bay Area, Sacramento, or San Jose. And when it hit. So there's lots of techniques for imaging these things. 55 miles across, 40 miles across, 20 miles across, that's third biggest in the US. But what's the biggest on planet Earth? That's still clear the depth. First biggest, 185 miles, right? So anyway, you don't have to memorize those in my class, but kind of interesting. You can pause and think about it. Right. So early on, slamming into Earth, and Earth was very malleable and stuff, so it covered up a lot of the early craters, but there were later craters too, and we get fewer and fewer craters with time. That would be a bad day. And we've got the surface of Earth. We don't see a ton of craters because it's warm inside and it changes. In fact, if you look at this, I'll let you look this up, it's kind of fun, who thought of plate tectonics and who, I'll give you hints, it's a woman, look her up, who really figured out, yeah, this is what's happening. So you can have the idea, you can go, hey, that looks like a puzzle, maybe those pieces were together before. And people thought, oh, yeah, it does look like it, but it doesn't mean it was, so where's the evidence? So look her up. Who really nailed that down and said, yep. In fact, there's a line here, the Mid-Atlantic Rift, that is spreading and widening, and you can image it about an inch every year. These were together. You've got biological evidence and geological evidence. And you got the smoking gun, you see it happening. It does widen ever so slowly, but about an inch a year. And there's some other evidence, like, hey, why do we always have so many earthquakes, which we'll talk about, and volcanoes around here? I mean, what's the deal here? What's going on? And the answer is, Earth is like a pie. I like berry pie. I pretty much like any pie. Nice warm pie with a crust, nice flaky crust. And the crust cracks. If you keep boiling it from underneath, if you leave it on the stovetop, might not be good. Things might move around. And you know it's warm inside. And so our crust, our lighter rock, is cracked, like a pie crust. And it's cracked into pieces. We call these plates. Here's a very large plate, smaller plate, and it depends on how you count them. I don't know, 8 large ones, so they might go 15, 16, something like that, right? You count the smaller ones, you check these out. And these things it's hot inside, right? Oh, wait a minute, oh yeah, that convection, right? Hot stuff going up and moving and spreading. These things will move. Over here, it spreads out. Ah, this is spreading out. And sometimes they come together and smush. So the movement of the surface. And for us, which is somewhat unusual, because our surface is lubricated by the water, etc., we have a softness, we have plates, and we call that plate tectonics. So let's write that up. Plate movement, or plate tectonics. And when you have plate tectonics, or when you have a berry pie with the crust cracked, stuff comes up through the cracks, right? Of course it does. And so you're going to have volcanoes and gas released. And if you have a soft spot in your plate, like Hawaii, then the hot stuff can come up through there too, even mid-plate, but along the cracks, certainly. And they can push together, and they can shift. And what does that give us? Let's take a look. Let's write it out. Let's really know it. Ooh, take a look at India. Do you see India over there on the left? What do you get over there? What happened here? This plate came up here, smashed in, crumpled. What do you get here? This is India, Sri Lanka, etc. It's fun to study a map and get to know it. For political reasons, economic reasons, geology, science, biology. It's all connected. Okay, and so let's write this up. Yeah, we've got hit a bunch. This got covered. Because Earth is warm inside. And before I go on, let me just say this. We're going to look at these things at other work. When we look at Mars, we can go, what does it have, what doesn't it have? Mercury, what does it have, what doesn't it have? Venus, what does it have, what doesn't it have? Those would be our primary other examples. What do they have? What went on? What went on here? And what you can see, Moon, is that if the surface, while they all, in our solar system, all formed at the same time, but if the surface didn't change much, if it wasn't warm inside, moving that crust around, etc., then it'll show a lot of craters. So an old surface, we say, born the same time, but a weathered surface might be better. Well, that'll be down here. Scratch that. We'll come back to that. An old surface is one that hasn't changed much. And so it's still heavily cratered. Hasn't changed much. So it's old, hasn't changed much. It's the way it was. And we will, when you see something that's heavily cratered, you go, hey, why am I looking at something older? Because most of that happened earlier on when it was messy. Not so much now, thank goodness. Now a new surface has changed and covered its craters. Pause and think. What's your first example of this? And your first example of this? Pause. What you guess? Moon, Earth. Okay. So, what are the ways we can change? Number 2 here is, we're going to throw up plate tectonics. And you might see a number of plates. But again, you can count the small ones or not count the small ones. I like the number 16. I don't know, 16 plates. You know, 8 big ones, 7. You know, however you want to count it. But there's a bunch of plates. It's broken up. And here's what's key, is that these plates are driven or moved by, pause and guess, pause and guess. Did you pause and guess? The convection, where? Pause and guess. In the mantle. The core being hot heats up that rock, it becomes softer, slowly rises up in a more complicated way, but rises up, cools, and sinks. And as it does that, it moves the layer on top around. Right? That warm berry filling, moving the crack around, if you will. What do we get? Well, we get a few things. We get earthquakes. For Earth, that's like a sneeze. It's just a little, you know, they come up against each other and then, you know, a little whatever. And since we got water, that sneeze can make for a wave. And that wave can travel across from Japan to California in a tsunami or tidal wave. Nothing to do with tides, but a tsunami. And for Earth, it's like whatever. It's like bath water, who cares? But for us, it's extremely dangerous, right? It's extremely dangerous. You see a big swell coming and you know there's an earthquake, etc. You go, because it will sweep out buildings and cars and you cannot fight it. And it's horrific. You can watch on YouTube, you can see tsunami and you can see it in action. And it's amazing. And I'm going to make a point about this. What else do you get? Tectonic mountains. I'm going to make a distinction between two types of mountains and craters. Craters being different. Tectonic mountains. Tectonic mountains happen when the surface, the crust comes together and kind of bulges up. And there's different ways, we're not going to get into that, but it bulges up. So when we see Earth, we've got that happening. And one other thing, and then I'll show you over here, you've got volcanism, which is coming right up, the next one. Okay. And I'll just say mountains and cracks. So the moving surface can create these things. And let me just put that up here, and then we'll take a peek over here at the picture. So 3, and it's really redundant here, but worth restating, volcanism, sometimes used with a U, the god Vulcan of fire. And this is important because it's going to lead us into our atmosphere. You get gas, atmosphere, and lava. Hot liquid rock quickly solidifies, and you see things like this, and geologists get all crazy because they've studied this, and they have conceptualized what went on to make that, and that's what's very cool about that study. So it's gas and lava released through cracks, and volcanic mountains, or volcanoes. I would say volcanic mountains, right? Volcanism. So let's take a look over here. Make sure you see what I want. Let's take a look at that picture. Right? That tectonics underneath can move the plates, and this water softening the crust and breaks into cracks. And what comes up? Well, hot stuff comes up, and this hot stuff can come up here. And it can build volcanic mountains. Right? So, and it can release gas, and it can release liquid rock, lava, solidifying into volcanic bombs. And why does that happen? Because look at this. This is separating, right? Because of this convection cycle. And look over here, it's also separating. So it's going to happen here too. But I just want to make a distinction that you can also have this separating and just have the surface crack. And so volcanic cracks, and what do they give? Of course, gas, lava. Right? So you can have that. But you can have the surface come together. Here they're spreading, but here they're coming together, aren't they? And so just keep it simple. I mean, you can get more detail if you want, but this picture here, the fact that the heat inside warms the softer stuff, and you've got layers of, this is the lighter rock, and then you've got the hot stuff rising, cooling, sinking, and this comes together, and what do you get? Crumpling, anything, any little hill, any mountain, things like that. Tectonic, no H in there, tectonic mountains. T-E-C, tonic mountains. And so that will certainly change your surface. Plate tectonics, the movement of the plate, giving mountains, and this volcanism. And I could have left them all connected, but the volcanism releases that gas and certainly changes the surface, and we're going to call that out in some of these worlds too. So let's take a look at some pictures real quick, and then we'll get to our last one, which is pretty cool. And hopefully when you go outside and you think about this, and you look for this, you start to take on a little appreciation for geology, but there's planetary geology. And so when you see areas of earthquakes and volcanoes all around this so-called ring of fire, you know why? Because that's where the plate boundaries are. But again, you can have hot stuff come up in softer areas of the plate. In fact, the plates move. And so if you've got a volcano, because there was a hot spot underneath it, and the plate moves, the volcano is no longer over the hot spot, and then that volcano is dormant. Some are still active, they go off, right? And you can watch them spark, and they're kind of cool if you know you're safe. But nature is powerful. The crumpling of the crust, look how small it is. Earth is smooth as a pool ball from a distance, but up close to a little tiny ant like us, it's huge. The Himalayas, remember I showed you India crumpling up? The Himalayas. I mean, amazing. But, you know, it's amazing what you can do if you go an inch a year over 1 million years, 10 million years, 100 million years, 500 million years, a billion years, right? We can't go 6 billion years. Solar system wasn't even formed, right? Solar system meaning Earth, Moon, stuff formed 4.6 billion years ago. We'll talk about that chapter 7. But you get this crumpling up, and if you, like I love to ski or snowboard or just throw snowballs or make snow people and creatures, you see people get really creative, then yay, the hot stuff made the cold stuff. I don't know, it's cool. Like, you can't even imagine it. Like, I can't, way down there, the hot stuff moves stuff around, crumples, goes up higher, and we got this, it's all 6 layers interconnected, right? So, what's that? Well, is that a tectonic mountain? The others were tectonic mountains, crumpling, where they come together. But then when they spread and the hot stuff comes up, you get volcanoes. You can tell it's big. It's even big to these guys. Where is it? You might guess. Kilimanjaro, right? But if you step away, it's like, it's just, just where the hot stuff came up. So don't just think about here. Don't just think about the surface of things. Think more deeply. That's what college is all about, right? Think about what caused that. The heat inside. Why is Earth still hot? How did it get hot? Releasing gas. Gas and lava. Shooting out the sides, volcanic bombs. Mount Etna, Sicily. Sparking, releasing gas, sometimes blowing. Oops. Sometimes being very dangerous. It's interesting though, isn't it? That the hot stuff, the stuff that's so dangerous, creating earthquakes, tsunamis, gives life too. So Earth is geologically alive, meaning that it's still changing. That's good. Gives a place, we look for environment. Where are there environments, if life started, where life could kind of take off? But with that, you have processes that can take life, give life, take life. Yosemite, we'll get to that. Yellowstone, right, is a pretty precarious situation. If this blows, we have a global catastrophe. Sorry. Hot stuff. What do I see? Where is it here? Here it is. The crust is stretchy. right? Hot stuff, if you're on a hot area, sometimes it comes near the surface, right? It can release. If you got water, it can boil the water. And then it goes poof. And then it builds up again, boil the water, poof. Geysers, right? Fresh water. And you can visit this. And visiting, it's gorgeous, but visiting and having a deeper sense of this planet that we live on, this planet, and there are other planets out there. Are there any like ours? There are some similarities, there are differences. That's the study of planetary geology, right? So that makes it kind of cool. You can sit and watch it, but don't just look at the poof. That's gets kind of boring. It's like, oh, whatever, I can do that with my hose at home. But it's getting heated, and you have that other picture, and you know, oh, there's a hot spot, and it's heating this water, and it's getting hotter and hotter and creating pressure, and then it blows, poof. You can set your watch to it, right? I mean, kind of crazy, and all that heat. Mount Lassen in California, north of Tahoe, Volcanic National Park. Really cool to hike along there, see lava flow beds. You can have a cinder cone. It's like kind of walking up sand. Look inside the little crater of the volcano, not an impact crater. So, you know, this is planet Earth. Get to know it, enjoy it. It's crazy. Releasing gas, some sulfur. And now we're going to talk about another way that Earth surface changes. The fourth way for Earth's surface to change. And here we go. All right, we've got 3. Let's make it 4. What is the fourth way for Earth's surface to change? So it's not too bad. Review. You get familiar with it, you got it. Okay. How did that place change? We'll talk about it. Number 4. Our surface, and perhaps the most obvious, is erosion. Leave something out, it erodes. Where do you erode from? You can erode from gas, like wind. You can erode from liquid, like water, rain. For us, obviously, water is a big thing, but there are other liquids. So maybe other worlds have different kinds of liquids. Oh, what about rivers? That'll really erode something, right? Liquid. And then solids. Again, any kind of solid rubbing on something will erode it. But Earth has really been affected by our water cycle. Water as gas, and other air as gas. Liquid, solid, like glaciers. And let's take a look. Right, let's take a look at those things. So we've got, let me just say, Yosemite, liquid, wind, rivers. Let's talk about Utah. Talk about Grand Canyon. And if you haven't been to these places, boy, it's really a treat. And once again, it's just so much more enjoyable to listen to a symphony if you have a sense of it. And I know friends that have a much deeper sense than I do, and they get more pleasure. So I try to study that. And this is Grand Canyon. If you can go, be safe, carry a lot of water, Spring is often good. You can get caught in a snowstorm. Lots of stories about this. This place, I would say, changed my life when I was a sophomore in high school. Really impacted me. It was so much bigger than my little world as in high school. And you may know how this formed. You might check it out. A little trickle of water, right? A little river, a little stream, cutting through the soft rock. And of course, there's wind, and there's gravity, and there's rain, right? But that cutting through the rock and creating this phenomenally beautiful canyon with layers and these geologic processes that are so hard to even think, forget about, don't forget about it. Astronomical time is hard enough, but then just Earth time, geologic time, is hard too when you talk about millions of years. That little by little, these processes happen. Just like studying things, initially it's confusing, and little by little it starts making sense, and you're playing Jimi Hendrix on the guitar. Yay. And there's Yosemite. Ice ages. Earth has gone through global warming and global cooling. It's true. Doesn't mean we're not impacting it. But there is a natural cycle. Ice age is a drag. I don't know, unless you know how to harness enough energy and be safe, right? A glacier filled this valley, beautiful valley, and polished these rocks and cut this dome in half to make half dome. And it's very cool. You can hike up here. You could backpack, camp out here, and then go up the next day. And you go up these cables. You never mess around with nature. People get in the water and they go over the waterfalls pretty much every year. I mean, people mess around climbing those cables. I've done it a number of times before you had to get permits and stuff, but you just don't mess around. It didn't seem particularly hard, and it was gorgeous. You don't throw rocks over, people could be climbing, right? So you think about things. But you think about what created this. You go up 2 waterfalls, big waterfalls on your way here. It's a beautiful hike. Don't drink the water. There's bacteria in it, right? But we'll use ultraviolet. Talk about that in the atmosphere to sterilize that water, okay? So it looks fresh, tastes fresh, but you can have bacteria give you gut problems for a few months. Okay, so anyway, it's a beautiful world. It has changed, Yosemite Valley. After a good snowfall, a good snow season, lots of rain. Utah, filled with water, soft rock, right? You got wind, soft rock, creating these arches in Utah. Again, carry lots of water, be safe. Look at that rock, don't want to stand there. How big are these arches? Here's a person, right there, right? So erosion, yes, Earth's surface has changed, and you have a sense, and this is a very good introduction. You want to go further than study a geology course and really get into some of those details, and it's important for construction and things like that. And next, we're going to talk about Earth's magnetic field. So I'm going to cut it here. I think we've got it done, and our discussion of Earth's magnetic field, I'm going to put before the atmosphere because it's going to be short. This I know was a little bit longer, but it's kind of cool. And in review, it gets simpler and simpler. So I encourage you to review all of that and how our Earth is so connected. And we're going to see now how Earth is so protected. And hopefully we got that. All right, until next time.